Alright, let's sketch the function f of x is equal to x to the power 4 minus 5x squared plus 4 with attention to the degree, the number of turning points, multiplicity, also known as the order, intercepts, maxima minima, refined sketch, interval positivity, negativity, intervals, limit increase and decrease. Okay, so this is a pretty jam-packed question. Let's start with the function, right? So the function here is f of x is equal to x to the power 4 minus 5x squared plus 4. What I want to do here to sketch this, I want to place this in the factored form. So if I'm placing this in the factored form, you need to use remainder theorem and thereby factor theorem to figure out what some of these factors are. Now, easiest way to do this, let's look at the integral zero theorem, where we can postulate some potential factors. So some potential factors here, we're going to be looking at the factors of the constant, which is 4, so 1, 2, 4, over plus minus the factors of the leading coefficient. In this case it's 1. So these are some values that we can test out. You can actually notice that if I do f of 1 here, you get 1 to the power 4 minus 5 to the power 1 squared minus 5 times 1 squared. That I didn't, sorry about that, not 5 to the power 1. 5 times 1 squared plus 4. And in this case, you basically will get f of 1 is equal to 0. So we know that f of 1 is equal to 0. This tells us that the remainder is 0. So according to factor theorem, x minus 1 is a factor. Okay, so x minus 1 is a factor. Well, if we test out f of negative 1 as well, because it's plus minus 1, we can actually notice that negative 1 to the power 4 minus 5 times negative 1 squared plus 4 will also give us 0. So x plus 1 is also a factor. Okay. Now, in this case, because it's x to the power 4, we need to divide by, you can either use synthetic division twice, or we can just do long division with the two factors, and we can find the product of the two factors. The two factors that we determined was x minus 1, and the other factor was x plus 1. Collectively, their product here is x squared minus 1, right? And what we can do here is, if we divide an x to the power 4 by an x to the power 2, our quotient should have an x to the power 2. So what I'm going to do here, because we can't use synthetic for non-linear divisors, I have to use long division. So x to the power 4 minus 5x squared plus 4, then I'm going to divide this by x squared minus 1, right? And if I divide this, I'm going to multiply this by x squared, so you get x to the power 4 minus x squared. I'm going to subtract these two, right? So these cancel out. You get negative 5x squared minus x squared. So you get negative 4x squared plus 4. Right, to match the leading term, the negative 4x squared, what I'm going to do here is I'm going to multiply this by negative 4. So if I multiply this by negative 4, you get negative 4x squared plus 4. And then when you subtract this, okay, so our quotient here is x squared minus 4, right? So collectively, the quotient is x squared minus 1 times x squared minus 4. So that's going to be x plus 1 times x minus 1 times x plus 2 times x minus 2. Okay, so this is your fully factored expression of f of x, right? And now what you want to do here is, using this fully factored f of x function, right, we want to also list down the degree and the number of turning points. Well, we can understand that the degree of the function here is 4, right? So n is equal to 4. The turns that you would expect in this function is going to be 3, right? So turns is just points of extrema. So we should expect a maximum of 3 turns here. Okay, so now that we have the 3 turns, we can understand that the a value here in this function, the leading term would basically be x to the power 1 times x to the power 1 times x to the power 1 times x to the power 1. Should be x to the power 4, right? So a here should be equal to 1. A would be greater than 0. So this is a positive even degree function, right? So this is a positive even degree function. And we know that because it's a positive even degree function, the n behaviors are going to be found in quadrants 1 and quadrants 2. Okay, so we're going to have the same n behaviors because it's an even degree function, and then they should be found in quadrants 1 and 2. Okay, so now that we understand that, and we have the possible number of terms. Let's take a look at the multiplicity, also known as the order, right? So you can understand that now in order to find the order, you need to find the roots. So let's find the intercepts. Okay, so the intercepts include, let's look at the x-intercept. You have to let f of x equals 0. So if you let f of x equals 0, then in this case you'll get x plus 1 times x minus 1, x plus 2. X minus 2 is equal to 0. So therefore x is equal to -1, +1, -2, and +2. Okay, so there's 4 x-intercepts, right? So there's 4 x-intercepts, and all of these guys have an order of 1. So because they all have an order of 1, then this means that it passes through, the graph will pass through each root. Okay, so the graph will pass through each root. All right, now let's create a sketch of this just to kind of demonstrate that. Right, well I'm gonna clear some space up here. Okay, so if we were going to create a sketch here, I'm just going to do that, let's get a different color. You guys don't have to create a legend for this, it's fine, right? So let's, if we wanted to create a sketch here, let's plot some points, right? So we have +1, we have +2, we have -1, -2, right? What can help us to design our sketch, we can also find the y-intercept, right? So I'm going to let f of x, well basically x equals 0, so f of 0, so in this case I'll just use my original function. So you can see that you get 0 to the power 4 minus 5 times 0 squared plus 4, so this is going to give us 4. Okay, so 0 and 4 is our y-intercept, so that's going to be, let's say it's like up here somewhere. Okay, and we stated that the end behaviors should end off in quadrants 2 and quadrants 1. Okay, so and you should pass through all these points, right? So basically it should loop around, do that. Whoops, let's clean that up a little bit. Okay, it should loop around and do that, right? Now because this is an even degree function, right, we need to understand that it's because it's concave up, there is going to be an absolute minimum. Right, so there should be an absolute maximum minimum associated with even degree functions. Now because the a value here, if you look at the function, a here is 1, because a is greater than 0, so therefore there should be an absolute minimum present. Now in order to find the absolute minimum, you also need to figure out the relative maximum minimum. Well, we know that there is a local maximum at 0 and 4. Okay, so the other 2 points that we need to look at in question are basically this point and this point. So one of them will be an absolute minimum. Once again, I just drew these without any kind of prior knowledge of actually doing this out algebraically. So let's actually calculate this algebraically and figure that out. So let's make some space here. All right, so I'm just going to erase this portion. Let's figure out our maximum minimum points. All right, so to find the maximum minimum points, right, this is going to be one of our terms. You can actually notice that there are 3 terms here. That's consistent with what we analyzed, right? So there will be a turn here. Let's call it turn 1, and there should be a turn here. Let's call it turn 2. Okay, and there is a turn here. All right, this is turn 3, but we already considered it. So let's take a look at this, right? X value of turn 1 should be the midpoint of these 2 x-intercepts. We're doing -2 plus -1 divided by 2, which is basically -1.5. Okay, so -3 over 2, which is -1.5. You want to find the y equivalent of this. You're doing f of -1.5. And you plug this into your equation, right? And in this case, this is going to give us -2.1875. So this is f of -1.5. And then the other point here is going to be f of 1.5, right? Because we can look at turn 2. It's the midpoint of 2 and 1, which is 3, and we divide this by 2, so you get turn 2 here is basically 1.5, and then f of 1.5, I'm going to plug that into there, right? F of 1.5, if I plug this in, you should get the same value, right? Because once again, it's the square, right? And you can actually see that here, because the squares would just kind of cancel out. So you can actually see that you actually get the same value. So I guess by luck, I just kind of pinpointed that they'd basically be the same value. So in this case, there is the absolute minimum is going to be the same as the local minimum. So the absolute minimum is basically going to be 1.5 and negative 2.1875, and also negative 1.5 and negative 2.1875. Okay, so that's what we have here. So this is negative 1.5, and then this is positive 1.5. Okay, so if we were looking at the domain and range here, right, so I'm just going to make some space out here. If I was looking at the domain and range, the domain here for all polynomial functions, x belongs to a set of all real numbers. The range here, y belongs to a set of all real numbers such that y is greater or equal to negative 2.1875. Okay, so that is the range. And intervals of positivity and negativity is just kind of referring to where is the function positive, where is it negative. Well, anytime that's positive, it's going to be above the x-axis, right? So all of these points here, right? So you're going to have to look between the intercepts. Well, we can see that interval positivity occurs when we have, and remember that positive means it's greater or equal to 0, so you can be inclusive, right? So x belongs to negative infinity and negative 2 bracket, right? As well as negative 1 to positive 1 here. So it's really useful when you have the sketch out, right? So union negative 1 to positive 1, union 2, positive infinity. Okay? An interval of negativity will basically occur between x belongs to, and you have to make these non-inclusive because it can be 0, 0 would not be negative, so this portion here and this portion here, union 1 and 2. Okay, so that's also good to understand, right? And the last part here, and this is a pretty large question, right? So the last part here is basically interval of increase and decrease. I'm just going to kind of erase all this out. Okay, so interval of increase and decrease. So interval of increase, you know what, let's do interval of increase in red. Okay, let's do interval of decrease first. Okay, so interval of decrease, you can see one here, there, right? So between negative infinity and negative 1.5, the turning point, right? So interval of decrease, x belongs to negative infinity, negative 1.5, union 0 and 1.5. Okay, and interval of increase, x belongs to, and you can check out this portion here, and this portion here, 1.5 and 0 union negative 1.5 and 0, and 1.5 and positive infinity. Okay, so that's your interval of increase, your interval of decrease associated with the slope of the secant. And that's basically our analysis of this function f of x is equal to x to the power 4 minus